Fabian Crusdt, Topological Invariants of Fractional Quantum Hall Systems, and to measure them. Oh, look, here it is.
Okay, thanks a lot. So thanks. I want to actually start the talk by thanking the organizers for inviting me to this beautiful Cambridge and give a talk here. I also live here. Okay, so I want to talk about topological invariants, and actually when I put together these slides for this talk, I realized how nicely actually few and many-body aspects come together if we think about topological invariants and how they can help us understand what's going on in these different topologically ordered systems. So the outline is as follows. In the first part, I want to give you some overview of topological order, what it means, how we can define it in different ways. So that's kind of a very theoretical part. If you feel this is too abstract, that's okay. Then you might want to start listening again in the second part, where I turn to the question, how can you measure topological invariance? In particular in cold atom systems, but in principle these schemes can be generalized to other systems as well. And then the first half here is about non-interacting systems. That is, you can think of that as few particle physics. And then I want to turn over and actually explain to you how quite generically we can generalize the concepts that we learned from few particle systems to correlated many-body systems. So here, this is really these Laughlin states, fractional quantum Hall systems like that. And again, I want to ask, how can we measure topological invariance characterizing these systems? And then the third part, that's more of an outlook. I want to make a few remarks about how we should think about topological order if we have statistical ensembles of states, that is basically finite temperature states. Okay, let me start with the topological order part. And I want to actually use something unconventional and start from the many-body aspect of topological order, and then explain how these topological invariants should be thought of. So let's take the many-body system and ask what are the different phases that this many-body system can be in. And then we realize that sometimes the phase changes, so we can have phases without any long-range order, so they're symmetric. Then we can change some parameter, and then at some critical point, we can have a phase transition to some symmetry-broken phase. And that's the typical Ginzburg-Landau paradigm. On this side, we have local order parameters that develop some long-range order. Okay, so this one system that we all know, which is exactly in this class, is the BEC, for instance. So here we have a state without long-range order. All two-point correlation functions decay exponentially. But if we go across some phase transition, we have some long-range order, and we have some complex order parameter, which is local. Now, if we have more general systems, that's where these topological systems are, it turns out we always have symmetric systems. So there's no symmetry breaking in general. And then, as I said, these correlation functions always decay exponentially in this symmetric, on the symmetric side. So we might be tempted to say, well, the ground state probably up to some local basis changes described by this unitary can be understood as some product state. So for instance, a Mott insulator we can think of as a product state of single bosons localized on different lattice sites. So that's kind of a tempting picture, but that's exactly what goes wrong if we have topological order. So a topologically ordered state is a state that cannot, by any local basis changes, be written as a simple product state. And what this basically means is that you have some long-range pattern of the entanglement, and that was really an understanding, I guess, that was coined by Xiaogang Wen, and they put forward this formulation in terms of these unitary transformations in these papers here. So that's these non-topologically trivial states, and these are states that are topologically non-trivial. Okay, now let me give you some examples and try to give more physical meaning to this. And first, I want to start with a very simple toy model from few-body physics. So imagine Alice and Bob, and they're very far apart in two distinct places. And let's say they share a Bell state. Okay, so up, down, plus down, up. So this state is entangled. And let's say all we allow are local basis changes of these guys. That doesn't change anything on the entanglement. So we can see the entanglement entropy is actually, we can think of as like an order parameter, a non-local order parameter in this case, which is actually extremely robust to local changes of the basis. And that's kind of the essence of topological order. Okay, so that's nice. Of course, this is kind of a too simple toy model. But if you think about a many-body system, Kitaev and Preskel actually formulated the analog of this simple toy model and showed that indeed the entropy, the entanglement entropy, does tell you something about topological order. So imagine you have a big system here, and you cut it into two halves, A and B. Then you can have, you can look at the entanglement entropy between these two parts. And then you make a cut, and let's say there's some local entanglement here where you make the cut, and that gives you a scaling of the entanglement entropy alpha times the length of this cut. So that's all these local entanglement, or these local correlations, if you wish. But in addition, you get a subleading term, which is a constant, and that stems from this non-local part of the entanglement. So in some sense here, we're really lucky, right? Because if we make the cut, by definition, there's no interaction. We don't get these local parts. So in this case, this log 2 is actually the only the long-range entanglement is the only one that's there. So that's all topological in some sense. Okay, so that's one example. Of course, now one question is how to measure this. That's kind of difficult. It's not. It's possible. In Markus Greiner's group, they have actually shown that that's possible to measure entanglement entropies, but it's definitely difficult. So let me turn to another example. And again, let me give you an example from few-body physics. So the example I want to give here is actually a very nice theorem, which is not very often mentioned. That's why I think it's nice to hear it, actually. And it says that, imagine you have a 2D system, just single band theory, and you have Wannier functions. Then in 2D, the statement is that these Wannier functions can be exponentially, or better, localized, if and only if the Chern number vanishes. So we've heard a lot about the Chern number, so I don't have to define it. It just says a band insulator is basically something that's super localized. The Wannier functions you can think of as exponentially localized. But then in the topologically non-trivial phase, for instance, in the integer quantum Hall, these Wannier functions, they have some non-local properties. And that's another picture of this fact that I was saying in the beginning, that local basis changes will never change this property. They will always keep them non-local in some sense. Okay. Now, of course, the question is, how does this Chern number come in? What does this Chern number have to do with this entanglement? And again, I want to give you some understanding of that. And so for this, I think it's kind of helpful to look at this definition. So imagine you have some state. Then what I'm saying is you can basically apply some unitary operation. It just describes local changes of the basis. And the topology of the state should not change. So if we want to define a topological invariant, it must be invariant under a very huge class of unitary transformations. Almost any unitary transformations, well, except they have to be local, but that's nasty to formulate. So let's say it should be invariant under almost all unitaries. So the invariants that we can come up with, we can actually go and look at overlaps. So imagine we have a system and we have an additional symmetry. So the simplest thing you can think of is say, take a 1D system, put it on a torus, and change the magnetic flux that you thread through this torus. Then, of course, by this, you cannot change the phase. You can basically, locally, you can always gauge this effect away. But it means that we can get a ground state wave function for every value of this phase that we thread. And what we can do is we can take a product over all overlaps of the ground state wave function at different discrete values, let's say j and j plus 1 of this symmetry parameter that we have. And I take this loop product, so you can see every bra and every cat appears exactly once each, okay? And therefore, this product is actually invariant under arbitrary unitary transformations, right? So that's a nice property of, yes?
What does the index j refer to? Is it?
So imagine you take this phi and you increase it in steps. So you have phi 1, phi 2, and so on.
Okay.
And now actually I'm taking the continuum limit of these j's. And then you can see that this, it turns out you do Taylor expansion, you get exactly the Berry phase out of this. You get x e to the minus I times the Berry phase. And so you can see that actually the Berry phase is something that's kind of very generically connected to some quantities which are invariant under unitaries. Okay, so that's a nice thing to realize. And these Berry phases are then connected to what we talked about before, the Chern number, by a winding. So it turns out the Chern number is the winding number of the Berry phase if we change, let's say, a second symmetry parameter and look at the Berry phase for every symmetry parameter phi prime. Okay, and that's a quantized integer that we want to measure.
And the assumption is that there's a unique non-degenerate psi for each value of phi?
Yes, that's true. That's a good point. So that's what we need to basically say that what we mean by psi. That should be a unique wave function. Okay, so that's kind of the overview I wanted to give, and that's basically a motivation to look at these geometric phases. And now the question is, how can we measure such invariants? If we look at geometric phases, or phase in general, one thing we're of course tempted to think about is interferometry. So let's begin with few body systems and apply the idea of interferometry to measure these Berry phases of some systems. So the simplest system you can think of is the Su-Schrieffer-Heger model. So let's say you have a Bloch band structure corresponding to particles hopping in this lattice potential with alternating hopping amplitudes T1 and T2 and so on. It turns out if you take the Bloch wave function with these two components corresponding to these two sites, you can calculate the Berry phase or the Zag phase, as people call it in this context. And it turns out, because of the inversion symmetry of this model around these bonds, this geometric phase is actually quantized. You can actually, if you plot these two components on a Bloch sphere, the inversion symmetry tells you that the Bloch vector will always be on the equator of this Bloch sphere. And it turns out that the Berry phase or the Zag phase is exactly the winding number of this Bloch sphere on the of this Bloch vector on the Bloch sphere equator. That's why it's basically quantized to 0, corresponding to 0 winding, and pi, which is 1 winding. Okay, now actually in Immanuel Bloch's group, and Monica was involved in this experiment, they realized exactly this lattice, loaded a BEC into it in the band minimum, and then they actually used two-component BEC. So they created a superposition of two quasi-spin components at the band minimum, and then they applied a magnetic field gradient. And what this does is it does Bloch oscillations, which we've heard a lot about, but in different directions for different spins. And once the spins reach the edge of the Brimmer zone, they basically recombine these two spins, and during this process, the different components pick up a relative phase, which exactly corresponds to this geometric Zag phase that one is interested in. So this is basically the basic building block of what I will talk about in the following. It's a combination of Ramsey interferometry with Bloch oscillations, which quite generically allows you to access these geometric phases. And this is, in fact, a very powerful thing you can play with now. So I told you in 1D systems you can measure these Zag phases. In 2D systems you can measure Chern numbers as winding numbers of Zag phases. So you have to just measure different the Zag phases at different values of some, in this case, the second parameter ky is second band momentum. But in fact, one can also go to even more complicated situations where there are bands with additional degeneracies. And that's something that appears quite often if, for instance, we have two different spin components, and okay, we can have spin orbit coupling opening some gap, but then because of time reversal symmetry, at some points we will always get Dirac points protected by time reversal symmetry. And that's exactly in the context of such system that topological insulators with Z2 topological order show up. And I want to discuss now a kind of a generalization of these Zag phases to two bands. Okay, and those are called Wilson loops. Okay, so imagine we kind of try to repeat the exact same experiment that I described before, just with two bands. So what we write down the equations of motions. Well, we get the IDT of the wave function is determined by the Bloch Hamiltonian describing these two energy bands, and then we apply force, and then here A is the Berry connection, which describes you how different basically describes you transitions between these bands if you're non-adiabatic. And what we're most interested in is the limit when the force is getting very large. Because in that case, F is large, you can neglect the band term, and it almost looks as if we have two completely degenerate bands now. And then, as I said, we apply the force. Let's say we start in the lowest band, but because we're so fast, we actually drive transitions also to the second band. And how much what the probability for such transitions is exactly described by the propagator corresponding to this equation, or the Schrödinger equation. So the propagator will be some P is some generalization of time ordering. It means path ordering along K. K changes as a function of time. And then basically you take e to the minus I Hamiltonian as A times T, and you get the propagator, which is basically called the Wilson line. Okay, so we want to measure this Wilson line, and that was done in another experiment in Emmanuel Bloch's group, where they realized exactly this honeycomb lattice with exactly this band structure, and measured basically exactly this transition amplitudes. Okay, so here's the measurement result. So this is on this axis we have the population in the first band. So at time equal 0, or basically we always start in the upper band, and then we apply a force and change the force, and these 3 different sets of curves correspond to different points in momentum space where we stop the evolution. Okay, and so if we're at weak forces down here, you can see there's almost no transfer. It's always very close to 1. That's because we're in the adiabatic limit. But if we go to very large forces, you can see that there's some saturation here. There's a slight decay here. Actually, this decay has to do, you can see the slight decay that has to do with transitions to even higher bands, not just these 2 that I was describing, but somewhere up there. And you can see that this saturation here, that's exactly where we should look at these Wilson lines. That's basically the large force limit that we're interested in. So this transition amplitude, or this value here, is actually a measure of this Wilson loop. Now what's interesting is the following. We actually go extremely fast, right? From here to here, the force is big, but you see there's still a finite population in the upper band. So this result is actually different from a naive Landau-Zener picture, which would suggest if you go infinitely fast, you transfer all your atoms to the upper band. And it turns out actually this value that you get, which is exactly the value of the Wilson loop here, is actually determined only by the geometry of this lattice. So it's a purely geometric quantity. Okay, so let me actually give you some more meaning to this Wilson line. What does it physically mean? I want to consider now Wilson loops. So what this means is just that I apply the force for exactly a time t corresponding to 1 Bloch oscillation. So time times the force should be 2 pi over a, meaning that a wave packet crosses exactly 1 Brimmer zone. Okay, and let's go and calculate. So this is kind of a hand-wavy picture, but it actually gives a nice way of understanding what we get. Let's calculate the dynamical phase that we get. So we're in this potential f dot r. Let's calculate the expectation value of this number and integrate it over time. That's the dynamical phase, right? And that's the phase we would expect that the system picks up. And in fact, what this means, in fact, it's not actually a dynamical phase. The reason is that we have time, it goes from 0 to t times f. And you can see t times f is actually a constant. That's always a constant number. So what we get out of here is actually nothing but the expectation value of the position operator times some prefactor 2 pi over a. And that means e to the I phi zac actually probes the polarization, which is exactly the center of mass position of the bands. And if we generalize this to multiband systems, and one can do that more formally, of course, one gets that the Wilson loop is basically the exponential of the polarization, and this polarization operator is now defined by the matrix overlaps of different Wannier functions. Alpha and beta now refer to the different bands, 1 and 2, and R is the position operator. Okay, so that's really basically what we're probing when we measure these Wilson loops. Okay, so with this, let me turn over to many-body systems and ask how can we measure such topological invariants as I described them now in correlated many-body systems. And of course, another question is how are they defined in the first place in this case. So in this, let's always consider some many-body systems could be fractional quantum Hall states. I want them to be gapped, so I want to have a gapped ground state of some system. And I want to start by asking how are the topological invariants defined in this case. So what we can do is we can take a system, again, put it on a torus, as sketched here for 1 dimension, and introduce a magnetic flux through the center of the torus. And then we can vary this flux from 0 to pi and look at how the, what the geometric phase is that the many-body wave function picks up during this process. And that's basically a one-to-one generalization of the Zac phase to this situation of a many-body system. Now, if we want to measure this many-body Zac phase directly, we have 2 problems. One is in the lab we would need to realize these periodic boundary conditions, and we need to thread this magnetic flux basically have a twist in these boundary conditions. That's kind of hard experimentally. And the second thing is we need to measure the overall phase of the many-body wave function. And this, again, is extremely hard, right? Because you can't measure the macroscopic phase of some many-body wave function, at least not easily. So both are actually kind of out of the game. So let's think of something alternative. And what actually helps is the following. So if you imagine you introduce flux through the center here, you actually induce an electric field which goes around the circle. So that's like a force, right? So the idea now is to exert a force on the many-body system in a controlled way. And we want to do this by putting an impurity particle into the system and then applying the force only to the impurity. And to couple this impurity efficiently to the many-body system, the idea is actually to bind it to a topological excitation of this many-body system. So imagine you have some quasi-particle, you bind it to this impurity, you get some new composite object which we call topological polarons, and then the idea is to apply these single-body schemes that I was talking about before, but this time to these composite bound objects, these topological polarons. And the nice thing is that if we have control over the impurities, for instance, we can think of impurities with two internal spin states. We can do interferometry using these different spin states of the impurity, and in that way probe the many-body system. So the generic kind of Hamiltonian that we can write down for this situation has a few terms. Obviously, there's the host system, there's the free impurity part, there's an interaction between the impurity and the host system, which we need to bind the impurity to the topological excitation. And then there's, for instance, the spin-dependent force, which we just need to do the interferometry and control this impurity particle. And then one limit that we're particularly interested in is the so-called strong coupling limit, which basically corresponds to the case where the impurity kinetic energy is very big, so the impurity can follow very fast the motion of the quasi-static quasi-particle. And in that case, it turns out you can write the wave function of this bound object, you can at least approximate it as a product state of a quasi-particle wave function at momentum q times the impurity, and that really describes how the impurity binds to this quasi-particle. And if we take this product wave function and go ahead and calculate the Zach phase or the Sperry phase, because it's a product, it turns out the topological invariant of this composite object is the sum of the quasi-particle invariant corresponding to this part and some part which corresponds to the impurity. But actually, because the impurity is just simply bound to the quasi-particle, this term is typically 0. And then we end up with this relation saying that the topological invariant of this composite object is exactly the same as the topological invariant of the quasi-particle. Okay, now I want to convince you that the topological invariant of the quasi-particle is really the same as, or at least encodes, the topological order of the many-body system that we're interested in. So let me start by looking at a quite simple example, which is a band insulator, let's say of free fermions. So imagine you have a few bands and you fill up an integer number of bands, alpha, and you calculate the many-body Zach phase of this, at this point even non-interacting system, but it's a many-body system. And it turns out the Zach phase is just the sum of all occupied bands, Zach phases of each of these occupied bands. Now imagine we actually create a hole excitation in one of these bands. Then of course the Zach phase of the hole in this band alpha is exactly the same as the Zach phase of exactly this band. It's a very simple relation. And what it means is actually that the Zach phase of the band insulator will be the sum of the Zach phases of all different kinds of hole excitations. In this case, the sum of all occupied bands of the Zach phase of these different kinds of holes. And this result actually carries over to a much bigger class of systems. So, for instance, in a fractional quantum Hall system, you have to sum over all different kinds of quasi-particle excitations, measure their topological invariance. We can also apply this to topological superconductors or some spin chains, for instance, to probe their topological order. Okay, but now let me really talk about fractional quantum Hall systems. So let's consider a Laughlin state at filling fraction 1 over m. Can be bosonic or fermionic, depending on whether m is even or odd. And first, of course, we want to understand the Chern number. So the Chern number of this state is actually 1 over m. So if you remember the transport experiments, you exactly measure the Chern number, and sigma xy is quantized in units of the Chern number. That's 1 over m for these fractional states. In fact, it's also related to the fractional charge of these particles. Turns out it's the quasi, this fractional charge in units of the bare electron or boson charge. So that's a nice relation. So what we want to do now to measure this this Chern number is we want to look at topological excitations. So imagine you have a whole excitation in this many-body system. Then we want to take an impurity, bind it to this hole, and measure the Chern number of this combined object. It turns out the Chern number of this combined object is exactly the inverse of the many-body Chern number. So it's also related to the fractional charge, of course, and it's given by m in this case. So, of course, we want to have some intuitive understanding why it's exactly the inverse. And there's a simple argument that we can make. So imagine you have some host particles here, and we have a quasi-particle. And the quasi-particle in the fractional quantum Hall really corresponds to a single vortex. And we bind the impurity to this vortex. Okay. Now, if we take this topological polaron, this bound object, around one of the host particles, we pick up an Harvard-Bohm phase, which is 2 pi, because it's one vortex. So basically, from the point of view of this quasi-particle, this looks like a magnetic field, which gives rise to this Harvard-Bohm phase. And now, if we want to look at the strength of this magnetic field, we realize that it's reduced by 1 over m as compared to the magnetic field of the host particles, because the filling, basically, the density of the host particles is 1 over m times the flux density of real magnetic flux that the host particles see. So the magnetic field is reduced by this factor of m. And if we look at the Berry curvature, that means that the Berry curvature is actually enhanced by a factor of m. And since the Chern number is an integral of the Berry curvature, the Chern number of this bound object will be m times the Chern number of the band, which is 1. Okay, so that's the basic reasoning. Of course, we want to check whether this is true. So we did some numerical simulations. And we looked at basically a Fermi-Hofstadter-Hubbard model. So we've heard about this Hofstadter-Hubbard model. Basically, we have atoms hopping in a square lattice with magnetic flux piercing every plaquette. And then these fermions have nearest neighbor interactions. And it turns out in this model, you can get a 1 over 3 Laflin type ground state for a certain set of parameters. So that's exactly what we looked at. And then we took a quasi-particle excitation, bounded to the impurity in the numerics, and calculated the Zach phase for different values of this basically the total momentum of this topological polaron. And the winding number of this guy, that was exactly the Chern number. And if you look at the winding, it's 1, 2, 3. So indeed, we get a Chern number for this composite object, which is 3. That is the inverse of the filling fraction, or the inverse of the Chern number of the many-body system. Okay.
How do you do this binding? So there's a term in the Hamiltonian that is like some local term that...
That's exactly right. So in fact, we just took a local density interaction between the two. Turns out that's enough.
Between the electrons and some impurity.
Yes. So we basically, you have a repulsion between the electrons and the impurity. And then, of course, I did choose the filling fraction such that there's one free vortex, basically, to which the impurity can bind. But then, once I choose the correct filling fraction, that this repulsive interaction is enough to bind the impurity. Although I should say that this bound state, the gap, the binding energy basically of the bound state is not very large.
So where's the impurity and where's the particles in this thing?
Sorry, this is just the bulk Hamiltonian I was writing down. So these are all the electrons. Without the impurity, yes.
Okay, the impurity is just
I should add it.
kinetic energy as well? Or?
Yeah, that's true. So it's actually hopping on the same lattice with some hopping constant t, which is comparable to this j, actually. Okay.
But you can't create individual quasi-particles, right? So
Yeah, that's, well, what I had in mind was Laflin's argument, basically. So imagine you have this bulk state, you introduce the magnetic flux quantum, then you create exactly one vortex. So I agree. So basically, the question how to prepare these bound states, that's a difficult one. I think it should be possible. You know, another way of thinking about it would be to take the impurity, throw it into the system, and give it enough time to equilibrate. So, for instance, you can create two quasi-particles, make sure one has enough time to go away, and then it binds the other one. And then we just do the experiments on this one that's left.
Numerical simulation I'm trying to understand.
Okay.
So it's, you're doing, like, you're diagonalizing this, what are you doing?
Yeah, so I'm really looking at the ground state. So that's true. So I use the fact that the total momentum of the system is conserved. And then I calculate the ground state of this combined system of all the fermions plus this one impurity for every total momentum. And then, I get something like a band structure in this many-body system. I get a nice ground state, and then I calculate the Chern number of this many-body ground state. That's exactly what I'm doing here.
This is a finite system,
Yes.
so there's really a discrete set of Ks that are allowed.
Yeah, that's true. But I actually twist the boundary conditions again. So I pierce magnetic flux through the torus. But actually, the discrete set would also be enough. Of course, to get the smooth curve, you need to have more of it.
Impurity is an extra fermionic degree that also hops on the same lattice.
That's right, yes. Yes.
It's mobile.
It's mobile, that's important. Yeah.
And how about, is there a spin degree freedom, or?
Here, no. These are spin polarized fermions.
Okay, but there's what kind of interaction is this? Is it nearest neighbor interaction, or?
Oh, between the fermions would be next nearest neighbor because they can't sit on top of each other. Okay, so let me. Yes, no.
So you look for quantum numbers of certain eigenstates and follow them. I'm trying to understand.
Yeah, that's exactly right. Yes. Well, not certain eigenstates. It's the ground state, which is a bound state in this case.
But then I think the question is that you have this bunch of fermions, and then you have this impurity, and then you look at the ground state Chern number,
Yes.
and it's okay, it gives you the Chern number, but how this is related to the curvature that you just measure from that specific impurity, how these two are related. And that's
You mean how the Chern number of the actual many-body ground state without the impurity is related to
So you have a many-body system. You have the ground state. You change the boundary condition, and you change the twist angle. You get Chern. You get some Chern number.
Oh yes.
You don't know.
Yes. Ah.
How this is related to just looking at the impurity.
Oh, I see. So basically, that's the thing, right? If you apply force, that changes the momentum of this quasi-particle, right? So that twisting boundary conditions and changing the force, applying a force to the quasi-particle is exactly the same. So that's why this gives you exactly the Chern number that you would measure of this bound object. Okay, let me use my last few minutes to make two remarks about topological order in thermal ensembles or in general mixed states. So if we have finite temperature, of course, we know that we have a density matrix which actually describes an ensemble of states. And in general, many of the states in the ensemble will have some long-range entanglement. So in general, it's very difficult to say what the topological order of something like this would be. So what I want to consider here, actually, I call them quasi-thermal states, basically where the density matrix we can write as e to the minus some effective Hamiltonian, where the Hamiltonian should be quasi-local. Okay, so it turns out this should be quite a large class of states. So I want to consider these. To understand what I want to do, let's first take a look at the case of zero temperature and how we can understand different topological states. It turns out at zero temperature, if I change my Hamiltonian adiabatically in time, then the topology of the state doesn't change. And that has to do with these local unitaries, because any time evolution with a finite Hamiltonian, which is adiabatic, is generated by a local unitary transformation. That is the local basis change. And the other way around, actually, in this paper, the authors have proven that if you have any local basis change, you can always write that as some adiabatic following of some local Hamiltonian. So if we follow a ground state adiabatically, its topology can never change as long as the gap doesn't close, where we're not adiabatic anymore. And this is exactly the kind of idea that I want to take over now. So let's consider a thermal state with some density matrix. Let's say a thermal density matrix. And let's ask, what does it mean to follow adiabatically this thermal density matrix? So we can look at the logarithm of rho, which basically gives us the spectrum of the Hamiltonian. and now adiabatically vary the Hamiltonian. If we're in this lowest state here, which is the most likely one, of course, we will always stay within this state. But then, because we apply some changes to the Hamiltonian, we actually apply some local unitary operation on this guy. If, on the other hand, we're somewhere in this manifold of these states here, and I adiabatically change the Hamiltonian, I will in general completely mix states within this manifold because they're not protected by the gaps between these different, let's say, manifolds of states. And therefore, if I change this Hamiltonian adiabatically, I get arbitrary mixed, basically unitary transformations mixing up these states within the manifolds, plus in addition local unitaries which mix these states with those states, but with this restriction that these are constrained to be local. Okay. And in this way, we basically can define equivalence classes of density matrices by saying that they should have the same spectral structure, and then one can be generated out of the other by a combination of arbitrary transformations within these manifolds plus local unitary transformations mixing, basically mixing all these states completely within the Hilbert space. And so one can apply this idea. I just looked at a simple toy model. So this is a 4x6 plaquette with 3 bosons hopping on them. And on these black dots, I used some attractive potential G. And I tuned this attractive potential G. If it's 0, I get one unique ground state with total Chern number equal to 1, because there's also magnetic flux of these guys here. That's like basically an integer quantum Hall states. Those are fermions. And then I get a manifold of states with a total Chern number of 9 in this case, and so on. And if we tune this G to very large values here, all the particles will be localized, and now the Chern numbers of these different manifolds of states that we get would be 0. And so that would be some simple example for basically a transition between a density matrix, which is topologically trivial, and then non-trivial here on that side and trivial on this side.
Where does it go from 1 to 0?
From
Chern number goes
roughly at this dashed line here. So you can see a gap. That's true. That's a finite size effect. If you look at the gap and you look at all different twist angles on this torus, it actually goes to 0. Okay, so another way to go is actually to generalize this polarization that I mentioned in the context of Wilson loops. You can also calculate that for density matrices, but it's not clear how this guy is related to these local unitary transformations that I mentioned here. Okay, with this I'm at the end actually. Let me summarize. So I showed you that there are very powerful methods to measure geometric phases or topological invariants for few body systems. And then in the second part of the talk, I tried to convince you that by coupling impurity particles to topological excitations, we can actually generalize all these few body systems and use that to measure many body topological invariants in highly correlated systems. And finally, I mentioned these open systems. But with this, let me come to an end and thank my collaborators, Eugene Demler, Michael Fleischauer, and Tracy Lee. And thanks a lot for your attention.
We have time for some questions. Already had quite a few.
So now that it's time for a question. This last few slides that you had on the demo one.
Yes.
So I was a little bit quick. I couldn't follow.
Mm-hmm.
So now in the last one, so from this model, what do you get? How do you define now the topological character of the thermal state?
So basically, the prescription would be you first look at the spectrum of the density matrix. You identify different manifolds. On this case, 1, 2, 3, 4. And then you calculate the Chern number of each manifold. And then you basically get a vector consisting of these different Chern numbers.
You populate the system at finite temperature, or you look at the zero temperature?
Well,
It simulates finite.
it doesn't matter in this case, right? Because this is just the temperature, inverse temperature term logarithm of rho. So, of course, if for instance, if I'm at 0 temperature, only this state matters. So in that case, you can throw away these. They're not important. If you go to super high temperatures, you're in a superposition of all, and again, it doesn't really matter. But in between, the statement is that there's a certain topological structure in the density matrix that you can probe in this way.
I'm going to translate what you say into to what I think you said. I'm restating it.
Sure. That's
So it seems to me what you said is ordinarily when we think about topological order, we say we have a family of Hamiltonians and we're going to look at the eigenstates of the Hamiltonians. Seems to me what you've just said is replace the word Hamiltonian with a density operator. Look at the eigenstates of the density operator.
yes, yes, I agree. Yes.
And then it has parameters.
Right, yeah. So I guess the most important thing, and that's the question Mohammed asked, is if, for instance, one of these gaps is closing here, since it's not actually Hamiltonian but the spectrum of the density matrix, that doesn't have dramatic effects for observables. There's no phase transition, right? If some of these gaps close like here. But still, you know, the topology of the density matrix changes in this sense.
But how this order is related to the normal order that we know?
Well, if I get in the limit of zero temperature, it's these two definitions are the same, right? Because at t equals 0, you just have one state, and the rest is all, you cannot think of them as degenerate infinite energy or quasi-energy here. And then that's just one limiting case of this construction. So, you know, you get some single state.
Say that it's like a weighted average of all these temperatures.
Yes, yes.
The density matrix. Sorry.
Well, let us thank our speaker one more time.